So today we're going to cover the last two types of tests for convergence, and the first one we're going to cover is probably my favorite one to use. It's called the ratio test, and I really like this one because it's pretty simple to use. You can use it with a lot of different things, and I like fractions, so it's kind of my thing. So if you have a series of a sequence A of n, right, it's just got to be a series of non-zero terms, basically, so not too bad. And then you have to do a ratio. So this series is going to converge if the limit as n goes to infinity of the absolute value of the an plus 1 term over the anth term is less than 1. It diverges if that limit is greater than 1. And it's inconclusive if it equals 1. So if it equals 1, it just tells you that you have to do something else. So you might want to try the integral test or a comparison test, see if it's a special thing that like a p-series or whatever, but you got to try something different. But the cool thing about these is that because of these absolute value bars, what am I doing? I got these tools over here now, right? These absolute value bars cancel out alternators. So you can also use these with alternating series. Absolute values. So I use this one a lot, and a lot of times it's my go-to. So like if you are very comfortable with a specific sort of convergence test and it works for a lot of different things like this one does, it's great to always try that right after you do the nth term test for divergence. But this one works really well for things that like exponentials and factorials, because those things are going to cancel out really well. So let's do a couple of examples to see how these work. Okay, so we're going to use the ratio test to determine if the following series converge or diverge, right? So the first thing we might look at is like the limit, right? Or maybe you're not sure what the limit is since you have an exponential over a factorial. Maybe you can't remember which one grows faster, right? So if we go to use the ratio test, we're going to do limit as n goes to infinity, right? And it's the anth term. So I'm going to go ahead and set up my fraction. So for the an plus 1 term, all you do is you take what you have and you plug n plus 1 in for where you have an n. And then in the bottom, right, it's just your an term. So you're just going to write the function exactly as is. Didn't exactly make my absolute value bars the right size here, and that's okay. That's what the pencil is for. Okay, right, so because we're doing a fraction, and we can actually drop the absolute values here because there's no alternators and these terms are always going to be positive as n goes to infinity, right? I can make this the an plus 1 term, right, times the reciprocal of the denominator. So then I'm going to group my like terms, just going to rearrange it. So then n factorial is n times n minus 1 times n minus 2, right, dot, 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 out to infinity. And then n plus 1 factorial starts with n plus 1. If I subtract a term off, I get n. Right, and then if I keep subtracting, right, n minus 1, n minus 2, right, keeps going on forever. So then I can start crossing some things out. So my factorials, right, these cancel out like that. So I'm going to be left with an n plus 1 in the bottom. Right, and if I subtract my terms here, right, this is really 2 to the n times 2 to the first. So my 2 to the n's will cancel out with my exponent rules. So this is really the limit as n goes to infinity of 2 over n plus 1. And that equals 0, which is less than 1, right? So therefore, this series from 1 to infinity of 2 to the n over n plus 1 factorial, right, converges by the ratio test. Right, so let's look at another example. Right, so we got a lot of terms going on, and so as soon as I see like a mix of things like this, it's nice to go ahead and start doing your ratio test. Right, because it almost looks like it could be geometric, but because of that n squared in the top, we don't know exactly what it's going to be doing. So I'm going to jump straight into my ratio test. And so for this, I'm going to put it in absolute values, but I'm going to just go right ahead and write my terms separately. So I'm going to plug n plus 1 in everywhere I see an n. And then I'm going to multiply by the reciprocal of my function, just to kind of get the algebra started a little bit. Okay. All right, so if I rearrange things a little bit, I'm going to actually split this into 3 fractions, just to kind of group my terms. Okay, so if I reduce everything, I can also drop those absolute value bars because everything's positive, right? From my first fraction, I'm going to be left with a 1/2. My second fraction, I'm going to be left with a 3/1, and then I'm just going to leave this as is. Now, as I take my limit, right, I'm going to get 3/2 from the first 2 terms, and then the limit of n plus 1 squared over n squared, since it's going to be n squared over n squared, right, that's going to be 1. So my overall limit here is 3/2, and that's greater than 1. So we can say that this then is going to diverge. I don't even remember what the original problem is. N squared times 3 to the n plus 1 over 2 to the n diverges by the ratio test. Okay, so we'll do a couple more examples just to make sure we've got the hang of this, and then we're going to quickly cover the root test, which is very similar, but just has a different sort of setup. Okay, right, so as soon as I see factorials and exponentials, my brain's immediately going to the ratio test. So I'm going to go, okay, that's not equals. We haven't started anything yet, right? So we have the limit as n goes to infinity of the absolute value of, right, if I'm plugging in n plus 1 everywhere I see an n, right, times, and then the reciprocal of my original function. Right, so again, everything's positive, so I can drop those absolute value bars. So I get 4n over 4n plus 1, right, times, that's going to be n plus 2 factorial, so that's n plus 2 times n plus 1 factorial, right, over n plus 1 factorial. So we can see that these things are going to cancel out. And if I reduce my first fraction, right, I'm going to have a 1/4 there, and then times n plus 2. And if I take the limit out to infinity, that equals infinity, which is certainly larger than 1, right? So this one is also going to diverge. So we're going to say the series from 1 to infinity of n plus 1 factorial over 4 to the n diverges by the ratio test. Right, and your brain might be saying, hey, I would have used a different test for that, and I also would have found that it diverges. That's fine. Unless the problem kind of specifies what you're using, you can use any divergence or convergence test you want to prove it, as long as you make sure it meets all the conditions. So now part D is just, it's an alternating series, so you could absolutely prove it in a couple of different ways. I just want to show you how you could use the ratio test to prove that this either converges or diverges, right? So there's lots of options. We could use alternating series test, we could use comparison, right? Anything like that. So if we use the ratio test here, we have the limit as n goes to infinity of the absolute value of -1 to the n plus 1, right, plus 1 all over n plus 1 times the reciprocal of my original equation. Okay, and that's going to equal limit as n goes to infinity. So those -1s are just alternators, and because of the absolute value, we're just going to cancel it out. So this is an instance where the ratio test is inconclusive. Right, so it doesn't work with everything. There are instances where you're going to get inconclusive results. So if we look back at this, this is just the alternating harmonic series, which if you watch the alternating series lesson, you know that converges conditionally. So you can always say that as well, just kind of an example of how the ratio test can sometimes fail. So the buddy to this, the ratio test, is the root test, and it's because basically it's the same thing, it's just you're using roots instead of ratios, hence the different name. So you still have a series of non-zero terms. So now you're still taking the limit as n goes to infinity, and it's going to converge if, this is a little different, it's not the square root, this is the nth root of the absolute value of the sequence is less than 1. It diverges if the nth root of the absolute value of the sequence is greater than 1. So those absolute value bars, again, they're just getting rid of your alternators, which means that you can use these for alternating series too. And again, it's also going to be inconclusive if that limit equals 1. So it's all of the same kind of conclusions that get drawn from the ratio test. It's just you're using the nth root of the absolute value of the sequence versus taking the absolute value of the ratio of the nth plus 1 term over the nth term. So this is not in the AP curriculum, but it's super helpful, especially if you can take a sequence that's entirely written as a power of n. It's just faster. You can still use the ratio test with all of these problems. It'll still work because of exponent rules, but this is just like a nice little one to have in your back pocket. So we're only going to do 2 problems to kind of show how it works. So we're going to determine convergence or divergence. We're going to obviously use the root test because we just talked about that. So I'm going to jump straight into this. So we have an n to the nth in the bottom, right? So that's called the Aleph function. So we're going to show what happens here. So I'm going to take the limit as n goes to infinity of the nth root of, and before I guess we should do that, we should rewrite this so it's a single value of n as an exponent. So I can pull that n exponent out, which would leave me with e squared over n, all raised to the nth power. Right? Technically it's an absolute value bars, but e squared over n is always going to be positive, so we don't really need to worry about those absolute value bars here. Right? Those are only in the setup of the problem in case you have an alternator. So, right, the nth power, the nth root, going to cancel out. And the limit as n goes to infinity of e squared over n is 0, right? And since 0 is less than 1, right, we can say that this series from n equaling 1 to infinity of e to the 2n over the Aleph function n to the n converges by the root test. Right, you easily could have used the ratio test here, right? You can use any of the tests that you want, just showing you a different way to do it. Right? Problem F is definitely written as an easy part to go ahead and use the root test for. Again, you could use the ratio test here, but you don't have to, or you could use whatever you wanted. Right? If you see a different way to do it, use a different way. So if we go ahead and take the limit as n goes to infinity of the nth root of the absolute value of, right, 3n plus 4 over 2n to the nth power. We're going to cancel the nth root and the nth power out. We can drop our absolute values because it's always positive here. Right, and then our limit is equal to 3/2, which is greater than 1. Right, and since we are greater than 1, right now this is diverging. So we can say the limit as n goes from 1 to infinity of 3 to the n plus 4 over 2n, not to the infinity power, whoops, to the nth power, diverges by the root test. Now you could have also used the nth term test for divergence here, but when you take the limit, you get 3 over 2 to the infinity, and that's a little weird to take that up. It's not totally inconclusive, but in case you're uncomfortable with that limit, that way you can use the